We had started the subject of image enhancement in the last class, and we had seen several types of image enhancement functions, okay, which are possible. Now today we are going to study some more image enhancement functions which are typically carried out on the images. But before that, I will show you some results pertaining to the discussions which we had in the last class, and what kind of enhanced image does it result, okay? These things we are going to show you in the form of a few results. Now, what we have here is the original image of a girl, okay? Here we are showing you the original image, and here I am showing you the image histogram for the same image. Now the definition of the histogram we are going to come little later on, but just to tell you, the histogram gives you a relative frequency of occurrence for the different pixels. So on this axis we are having the various pixel intensities starting from 0 to 255 is the last one. So that means to say that the image intensities are in the range of 0 to 255, and on the y-axis we are indicating the count of the number of pixels occurring in the particular grayscale level, okay, and it gives us a curve of this nature. Of course it's a discrete curve because we are having discrete set of points in the range of 0 to 255, okay. So this actually gives us the image histogram. Now, why the histogram is also important for the purpose of image enhancement, we will be explaining this aspect a bit shortly, okay. But this is just to show you the nature of the histogram which we have for this original image, okay. Now we had discussed that how one obtains a negative image from a positive one. So in order to get a negative image, the transformation which we had applied was that the original image was having intensity U and the transformed image was having an intensity V, and the characteristic was given as V is equal to L minus U, where L is the maximum permissible intensity. So we were having a transfer function of this nature in this direction U and in this direction V. So as a result of applying the transformation of this nature on this original image, this being the original one, we get a negative image which looks like this. This is the negative image of the original one. Okay. Now we had also discussed the various types of transformations. So typically we had considered a case where we were having three straight lines, alpha, beta and gamma, having slopes alpha, beta and gamma, and we had considered some special cases, okay. One special case was where alpha, that is to say the slope of the line in the range 0 to a was equal to 0. The slope of the line in the range of B to L was also 0, and within the limits A to B we were having a slope beta. So obviously beta is greater than unity, as we clearly see here, because the zone from A to B is being mapped into the grayscale value of 0 to L. Alright, so in this case what we are doing is a linear contrast stretching, okay. In the zone of A to B we are having a linear contrast stretch such that the intensities in the range A to B in the original image, okay, gets translated to intensities in the range of 0 to L, okay, in the output or the processed image. Now from the original image, okay, we had applied such a kind of linear contrast stretch, okay, and we got this image, okay. This is a result of having a linear contrast stretching in the range of 30 to 180. So that means to say our A was equal to 30 and B was equal to 180. Look at this curve once again. A is equal to 30 and B is equal to 180, okay, and we have stretched it from 0 to 255 over here, okay, and by having that we have obtained a linear contrast stretching, okay. Just compare this image with the original one. This was the original, all right, and this is the image that we get after carrying out the linear contrast stretch. So clearly you can see that there is definitely some improvement in the contrast of this image, all right. Now we had considered some more special cases of this one, okay. For case 2, where we considered alpha equal to gamma equal to 0, all right, we had considered a special case where we had decreased the spacing between A and B, all right, and in the limit when we have A equal to B, it results in a threshold function which we had shown in the last class. So as a special case of this, we considered A equal to B, and that we had defined to be as T, where T is defined as the threshold, okay. So this being the intensity of the original image and V being the intensity of the processed image, the transfer function which results is of this nature, all right. And we had taken the result, okay, where we had defined the threshold T equal to 75, okay. So that means to say, you have a look at the original histogram, okay, and somewhere over here maybe that if this is the point where we get the grayscale value equal to 75, anything which is less than this, okay, is being treated as intensity level 0, and anything which is above 75 is treated as intensity level equal to 255. And by applying the threshold T is equal to 75, we have simply binarized the image. The original image has now been converted into a binary image. So whatever you are seeing in white, okay, is having the intensity equal to 255, and whatever you are seeing in black has been made intensity equal to 0, okay. Now we had also discussed that how one can apply intensity slicing, and there we had discussed two things: intensity level slicing without background, okay, and intensity level slicing with background. So whenever we were having the curve of this nature, okay, that means to say when this pink curve was being followed, okay, so I refer to this one. In this case, what we were doing is only the intensities in the range of A to B was converted to intensity equal to L, okay, the maximum intensity, and the rest, that is to say all the background pixels, were forcibly made equal to 0, all right. So by destroying the background, okay, we can have an intensity level slicing in the range of A to B, and this is exactly what we did over here. This is intensity level slicing, okay, without background. Now the slice range, in this case what we have chosen, A we have chosen as 80 and B has been chosen as 150, all right, and we have converted all the pixels which are in the range of 80 to 150 to intensity value equal to 255, so 225 rather. So whatever pixels are there having the intensities 80 to 150 has been made intensity equal to 255, okay, and all the background pixels, okay, no matter whether it is above the value of B 150 or whether it is below A which is equal to 80, they have been converted to 0, all right, and we get this kind of an image, all right. So this is without background. This is slicing without background. and intensity slicing with background is like this, okay, where we trace the green curve, meaning in the range of A to B, as before, we are converting the intensities to this level, okay, but in the other range, that is 0 to A or from B to L, okay, we are not changing the intensities of the original image, okay. So here the slope in the range of 0 to A or in the range of B to L is exactly equal to unity. All right. So by having a transfer function of this nature as traced by this green curve, okay, we get the result like this. In this image, okay, A is made equal to 50, B has been made equal to 75, okay, and the rest of the points, okay, are being kept at the same intensity. So whatever you are seeing in these white patches, okay, whatever you are seeing in these white patches over here, okay, these pixels are in the range of 50 to 75 and they have been made white, okay. Actually their intensity values have been converted not to 255 but we have converted it to 225, okay, so that you get a distinction from the absolute white and the converted values. So any pixels in the range 50 to 75 have been converted to 225 and the rest of the pixels are being maintained at the original intensity level. All right. So these are some of the results which we are showing. All right. Now in the last class, whatever image enhancement techniques we have learned, okay, they were basically enhancing the images, okay. That means to say we were finding that in most of the cases the dynamic range of the image, okay, was getting stretched or the dynamic range was getting improved. Now at times in some of the images we need to, don't feel surprised, we need to reduce the dynamic range instead of increasing it, okay. I tell you a simple application of this, okay. You take an original image, all right, and you convert the image into its transform domain image, all right. So that means to say from U of Mn you convert it to V of Kl by applying any unitary transformation. In V of Kl, what you will get is the various transform coefficients, right? And many times we get the images like this. All right. Now obviously V of Kl will be defined like this, okay. K equal to 0 and L is equal to 0 point is normally over here, okay, and K increases in this direction, L increases in this direction. That's how I proceed. But I had also told you in course of our discussions on the transforms that we can transform or we can translate by applying a translation. We can translate this corner point, okay, having K equal to 0, L equal to 0 coordinate can be translated to the middle, that is to say the central point. Now around the central point, supposing we are plotting the values of various VKLs, that means to say the transform coefficients. Now usually it is found that the transform coefficients, okay, near the center they are having quite high values, okay, as compared to the transform coefficients in the rest of the places. So as a result of that, if you are translating those high values or rather high magnitudes, you take the magnitude of VKLs, okay, and the high magnitudes you just try to represent over here, you scale it down to 255, okay, the scale of the maximum intensity, okay, and you try to represent the image, you will find that only a small zone centered around this central pixel, okay, will be having some high intensity values. Whatever I am showing with red, okay, they are indicating the high intensity values in the sense, or rather the high values of transform coefficients, okay, whereas the rest of the coefficients, okay, are so small that if you are scaling these things down to 255, you will get an image, okay, from which you will not be able to make out that what are the values of the other pixels, okay, which are around, because everything will appear as dark, okay, and only in a very small zone centered around 0 you will find that the intensity is high. So that means to say, what is happening is that some of the transform coefficients are having this much of high values, and in comparison with this, the other coefficients are having values like this, okay, and we are only taking this, we are neglecting all others. So in this case, what we should do is, we should do a range compression, all right, such that the lower intensities, okay, are highlighted more as compared to the higher intensity regions of the picture. Let me tell you once again, what we will try to do is, okay, that the lower intensities will be highlighted as compared to the higher intensities. Rather, we should get a transfer function of this nature. If this is the u-axis, okay, the original intensity axis, and if this is the v-axis, which is the intensity of the processed image, okay, if we get a curve of this nature, okay, what results? The lower intensities are stretched and the higher intensities are compressed. So if we can do like this, okay, then possibly instead of having a very small zone of bright intensity, okay, we can possibly have, okay, a larger zone, okay, where we can observe, okay, some more pixels, okay, properly. So basically in this case, what we are doing over here is a dynamic range compression. So we are forcibly bringing down this much of high intensity level, okay, and we have forcibly brought it down, okay, so that all the other intensities are visible in compared to this. But we haven't brought down it linearly. We had obviously applied a non-linear transformation, all right. Obviously this nature of transformation is a non-linear transformation that results. Now can you suggest that what kind of a transformation function I can take so that the transfer characteristic looks like this, looks somewhat like this? Yes please? Two straight line combinations or any curve. Somebody was suggesting a parabolic curve, or rather part of a parabola. All right, I think a very good mathematical function which will give us a curve of this nature is a logarithmic function. Okay, a logarithmic function gives a very good stretching in the lower values, okay, as compared to higher values, or rather the higher values are compressed in a logarithmic function. Okay. So if we design our transfer function like this, say the processed image is having intensity equal to V, and if we make it equal to C log to the base 10, 1 plus modulus of U, where U is the intensity of the original image, okay, then the transfer characteristic that results from this equation, okay, will give you a curve like this, which I showed you, okay, and clearly in this case there is a range compression. But mind you, range compression obviously in this expression, C is nothing but a scaling constant. So C is a scaling constant. All right. Now, this kind of a transformation you can think of using where some intensity values are very high as compared to others, just to bring the level down. But if you are applying these transformations, okay, on a normal image, okay, where the intensities are not distributed like this, okay, where the intensities are relatively closer to each other, okay, for such kind of images, if we are forcibly using a compression, okay, the image quality is clearly going to deteriorate, okay, and this is what I can show you now, okay. Again, for the same girl image, just see, this was our original image, okay, and by applying a logarithmic compression, what we will get is a much poor contrast image as compared to this, okay. See the result. This is a logarithmically compressed image, okay, and clearly the contrast for this image is quite poor, okay. All right. Now, let us see some more techniques, okay, for image enhancement, or rather not image enhancement alone. We are in general discussing about the point transformation. Point transformation in the sense that point by point, where, okay, point by point we are modifying the intensity values of the pixels. All right. So because we had defined in the last class that the neighborhood region which we have chosen for the transformation function, basically we were considering a function of this nature. The output intensity V was some function of the input intensity U, and we were defining this function over a neighborhood area, okay, and when that neighborhood area is of size 1 by 1, we are getting a point transformation. Now, some other interesting point transformation that results is, okay, where supposing we have two images. We have got an image, okay, whose intensities I am writing as a function f1 at the point xy, okay, and we have yet another image, okay, whose intensity function I am writing as f2, okay, at the point xy. So I am taking two images, okay, whose intensity functions are f1 and f2. Now at a particular point xy, if I subtract the intensity of the first image, or rather intensity of the second image from the first one, okay, what I get is a difference image. An image which is a simple point by point difference of two images, okay, and as a result of that, obviously a new image results. So the output image that we get in the process, let me call it as G of xy. So the output image is having intensity G, okay, defined at the point xy, and which is equal to the difference of two images, f1 and f2, okay. So this is an image subtraction. This is called as image subtraction. Can you suggest some use of image subtraction? Is it only data compression? Circuit checking, excellent. That is one application. Moving object detection, excellent. Anyone else wants to suggest?
Security.
All right. I mean, we have already got some good suggestions, okay, about what kind of application results from this image subtraction. Now, supposing we have a model image, okay, the image of a printed circuit board, an assembled printed circuit board, okay, where supposing this is the printed circuit board, and we have a number of components, okay, which are to be mounted on the printed circuit board. Okay, like this there are a number of components, and in our model library we have got an image like this, that is how an assembled PCB should look like, an assembled printed circuit board should look like. But supposing the actual printed circuit board which has come out of the assembly, okay, looks like this, where we find that this part is there, okay, this component has been mounted, we find that even this component also has been mounted, okay, this component has been mounted, supposing this one also has been mounted, and some smaller components like say this one is missing, but we have mounted the other ones. We have mounted this one as well as this one, so all others have been mounted. Now I take this as my F1 image and I take this as my F2 image. If I subtract F2 from F1, what do I get? I get only this missing element. Okay. So for changing a printed circuit board, okay, for the presence of missing components, okay, if we just do a simple image subtraction between F1 and F2, okay, we can identify the missing component. Okay. Somebody has mentioned the application in case of moving objects. That's also an excellent application. Like say for example, we have got two frames of an image, all right, and there is an object like this, okay, in the first image, and the same object we would like to see that whether this object has moved, okay, in the second image or not. Supposing this is a second image and this has been obtained after some time, okay, maybe that at time t is equal to t1 we had obtained this image, and at time t is equal to t2 we have obtained this image. Now we would like to know that whether this particular object is moving or not. Simply what I will do, I will subtract, I will take this as the image F2, I will take this as the image F1, and I will subtract F2 from F1. If I find that the result of subtracting F1 and F2, okay, results in an image where all the intensities are 0, I can conclude that the object is a stationary object. Okay, this object hasn't changed its position. But if I find that the image has got some elements, okay, which are non-zero, then definitely there is a change, okay, by which we can detect the moving objects. Okay. Now somebody was telling that for the, I mean there are other applications also, like say in the case of remote sensing pictures, okay. Supposing you take an image, okay, of a particular area, some satellite image of an area before the rainy season, okay, and then after the rainy season when the crops are there, you take the image of the same area, and then from the difference you can find out that how much of area, okay, has been converted to a crop area, okay, in the, I mean from the satellite picture, okay, or rather the difference. What kind of differences are you observing in successive images, okay, that you can see by simply subtracting one image from the other. But obviously, please keep in mind that the subtraction that we do, okay, may not be always possible for change detection. In this case, we are all the time assuming that the coordinates of the model image and the coordinates of the actual image, they are perfectly matching. So I am all the time assuming that the printed circuit board, if this is the test and this is the model, I am assuming that the test image and the model image, they have been perfectly matched in their coordinate positions, okay. Only then we can apply the image subtraction, okay, and get a meaningful result. If it is not, then obviously the change detection becomes difficult, okay. But where the coordinates are perfectly matched, one can use this image subtraction technique, okay, for the purpose of change detection. Now we will see some very interesting way of improving the contrast of an image, okay, and what we will be doing there is a method which is called as histogram equalization, and we are going to discuss this today. Let me tell you what it is. Okay. Now, how do we get the image histogram? I have already defined the histogram. Okay. Now, we have a digital image where the gray levels are in the range of, okay, all the gray levels I have assumed that they are in the range of 0 to capital L minus 1. Okay. Now, the histogram is nothing but a discrete function which is defined like this. I will write it as follows: P of uk equals nk divided by n, alright, where uk is the kth gray level and nk is the number of pixels having kth gray level. What is this n? The denominator term? So the denominator term n is the total number of pixels. So if for every gray level, okay, that means to say if we compute this, okay, for k is equal to 0, 1, 2, etc., all integer values in the range of 0 to L minus 1, if you are computing this, okay, then what you are getting is a discrete function of PUK, okay, and this discrete function is defined as the histogram of the image, alright. So typically a histogram will look something like this. Supposing on this axis I am plotting UK and on this axis I am plotting this nk by n, alright. Nk by n, its maximum value could be equal to 1. So definitely nk by n is a function which is going to lie in the range of 0 to 1. And uk, supposing they are in the range of u0 to ul minus 1. Now the histogram could look something like this, may look maybe of this nature. Okay, or the histogram may look something like this, depends on the image. For some images we may get the histogram of this nature. Okay, this is UK, this is same nk by n, or we may get the histogram possibly of this nature. Okay, this is UK, this is nk by n. Now this is say histogram number 1, this is histogram number 2, and this is histogram number 3. Now what do we clearly observe? In histogram number 3, what is the conclusion that you can draw about the image?
Low intensity.
That most of the pixels are in the lower intensity. Although our total intensity is varying from 0 to L minus 1, okay, most of the pixels are clustered, okay, in a small zone like this. In a small zone like this we find most of the pixels are there. So that means to say we are not effectively using the entire dynamic range of grayscale values. Look at histogram number 2. What do we get? Most of the pixels are in the higher intensity regions, okay, and very few pixels are in the lower intensity region. Again, for this image also we are not making a good use of the dynamic range. Look at the histogram number 1, okay, supposing this is the maximum intensity corresponding to L minus 1, this is the intensity for 0, okay. Now we are finding that most of the intensities, okay, are in the middle region. So that means to say most of the intensities are in the gray values. Okay, neither too dark nor too white. Okay, even here also we are not making a good use of the entire dynamic range of pixels. Okay, so definitely by observing this histogram number 3 or by observing histogram number 2 or 1, one conclusion which we can draw is that if it would have been possible for us to modify the histogram in such a manner that we could have utilized the entire dynamic range from 0 to L minus 1, okay, then one can obviously say that the image would have looked better, at least from a contrast point of view. So what we should try to do is, okay, to get an image where the pixels, where the distribution of the pixels which we are having, in this case it is the distribution of the pixels, or rather the relative occurrences of the pixels which we are plotting over here. If the relative occurrence of the pixels at the various intensities, they are more or less uniform in nature. I am not saying exact, but if the distribution is more or less uniform, okay, then possibly the image contrast should increase. Okay, so from these images we may like to get an histogram of this nature. Say this is the UK axis as before, and this is NK by N, and we would like to get a histogram ideally which should look like this. If we had got a histogram of this nature, then one can say that the probability of occurrence for all the gray scales, for all the intensities in the range of 0 to L minus 1, they are more or less equal. And if we can get a histogram like this, okay, or close to this, we will call this approach as a histogram equalization. So that means to say that for the processed image whose intensities are V, okay, for the image V, its histogram should look like this, despite the fact that the original histogram, okay, that is to say histogram of the image U may look like this, 3, 2 or 1. Now how to obtain, that means to say that for the image V, we would like to obtain a histogram like this. Alright. Now the question is, how do we do it? Let us see. Now, one thing, look at the histogram once again, or let us see an actual histogram from the image. Say take this girl image where this was our histogram. Now clearly these are all discrete values. For all the UKs we are having some discrete values of NK by N. Now if we keep on reducing the difference between UK and UK minus 1, okay, if this difference UK minus 1, this tends to 0, then what does it result? Instead of a discrete function, it becomes a continuous function. So a continuous function would look something like this possibly. Okay, see this is 0, this is L minus 1, this I will no longer call as UK because now it has become a continuous function, so I will call it as U, and this is the NK by N, okay, or rather the relative probability of occurrence. Now for the continuous case, can you tell me that what name should I give to this curve? For the discrete case I was calling it as histogram, or rather I was calling it as the frequency of occurrences. if I make it a continuous function, what should I call? This results in a probability density function. So this curve will give me the probability density function, okay, or rather PDF. So the PDF will be of this nature. Okay. Now let us consider an image pixel, okay, whose intensity value is u, and I consider u is greater than or equal to 0, because as you know, the image intensity cannot be 0. I mean cannot be negative. Okay, it can be either 0 or greater than 0, and consider that this pixel value u greater than or equal to 0 is a random variable. Okay, I am writing in short form as RV, having a continuous probability density function P of u. Okay, so this is the PDF. This is the probability density function of u. All right, and I also consider its cumulative distribution function, which is called as CDF. Okay, which can be written like this. I am going to write it in terms of a dummy variable w as f of w with respect to u, which is being defined as the probability that this dummy variable w is less than or equal to u. Okay, so this gives me the definition of the cumulative distribution function, or the CDF. Okay, probability that w is less than or equal to u, okay, which is written as follows: f of w with respect to the variable u. All right. Now, obviously, if we have got a probability density curve like this, if this is the nature we get for PUU, okay, we would like to design a PUV or PVV which is uniform. So rather, we would like to design a probability density function PV, okay, with respect to the variable v, whose nature will be uniform. V should be uniformly distributed. Okay, that is what I want. Okay, so we should get a continuous curve like this for the PDF of V. All right, the PDF of U is like this, and the PDF of V should be like this. So obviously, we have to apply a point transformation, which is of the form V equals f of u. All right. Now, I really don't know what is this f. I have to design that in such a manner that v has got a uniform probability density function. Now, let us choose the function f, okay, like this, or rather, if we take the transformation function of this nature, I define v as f of u, which if I write as the integral of pu with respect to the dummy variable w dw, and I integrate it from 0 to u for all u's in the range of 0 to 1. Okay. Then what am I writing in this integral expression? Can anybody tell me? This integral expression gives me the probability that w is less than or equal to u, and this, according to our definition, is the cumulative distribution function, or rather the CDF. My CDF has been defined like this: probability that w is less than or equal to u, and I would get that by simply integrating the probability density function within limits 0 to u. All right. So the transfer function which we are going to choose, okay, should be a cumulative distribution function. Okay, so that if I get a probability density function, if my PDF is something like this. Okay, my cumulative density, my cumulative distribution function for this one may be of this nature. Okay, where this was our u, okay, and this was the PU of u. Okay, this was the probability density function, and the cumulative density function, okay, will be like this. Rather, this I will write as FU u, and on this axis will be my u. Or rather, this FU of u I have defined as the, as what? As my V, as the, the transformation function itself has been defined as V is equal to this. So that means to say this can be written as Fu. Of course, we have to write it with respect to the dummy variable W in this case, which I can substitute by U again. So this is the cumulative function, or rather I can write it straight away as V. So if this is U and this is V, what does it result? It gives me a transfer function, V with respect to U. So the transfer function is of the nature of the cumulative distribution function. Now it can be proved mathematically, okay, I am leaving that proof to you as an exercise, okay. It can be proved mathematically that this function V, okay, has got a uniform probability density function. V has got a uniform probability density function. Alright? So that means to say what? That if we design a transfer function which is same as the cumulative distribution function of the input variable, okay, then the output that we get, okay, the output variables which we get, they are uniformly distributed. Their probability density function is uniform. And obviously we will get, if we try to take the histogram, now histogram will be nothing but the samples of the continuous probability density function. So the samples will be of this nature. And we will get an histogram equalized image. Okay, I will show you the output. This was our original image. Okay, this is the original image, and the histogram equalized image looks like this. Alright, you can clearly see that there is an improvement in the overall contrast. Just see, this was the original image. Observe the histogram equalized image. There is definitely a contrast improvement because the dynamic range of intensities have been stretched. Now, instead of having a histogram of this nature, where you can clearly see that most of the pixels are, rather to say, cluttered in this zone, okay, whereas the zone from here to here are not effectively utilized, okay. But if I utilize this zone, rather all the image intensities are utilized properly, we get the histogram equalized image like this. Now, one thing which should be told in this connection, that the histogram equalization method is obviously quite useful, alright, but the method of histogram equalization does not give us a contrast enhancement interactively, okay. We cannot have an interactive contrast enhancement because histogram equalization will only give us a single solution, alright, and histogram equalized image, in that we will get only a single solution like this, okay. Now, if it could be done like this, supposing for an image we have the probability density function, or rather the histogram, whatever way you say, supposing the PDF is of this nature. And so this was the PDF of U. So this was U and this was PU of U. Now it may be so that our objective is to design a contrast enhancement such that the output function V that we get, okay, should have a probability density function maybe of this nature. Supposing I want it to be this way, I want that the probability density function of the original image was like this, okay, and I would like to make the probability density function of this nature. This is what I want for V. But obviously my histogram equalized image will not give me a probability density function of V having this nature. Okay? The probability density function of V will be uniform, but I want it to be this way. Okay? So how we can design a transformation such that this nature of a histogram, okay, gets converted to this nature of a histogram. This is the histogram of the input image, okay. This is the histogram of the processed image. So again, my task is to design a suitable transformation so that for the processed image I get this nature. Well, the task is very simple. What I will do simply is that I will define a function W, okay, such that W is defined like this. W is the integral of Pu for a dummy variable x dx within limit 0 to u. So what I am doing? Again I am taking the cumulative distribution function of u only, okay, and I call this as Fu u. Alright. So I am equalizing the image. I am histogram equalizing. Now I am taking the same function W, okay, which satisfies this relation Pv y dy within the limits 0 to v. If the function W is doing what? It is equalizing this image u, isn't it? And if I take this distribution, this uniform distribution, I can get a uniform distribution by equalizing this V image also. Although really speaking we haven't got the V image yet, okay, but if hypothetically if I had got a V image, okay, I could have equalized the processed image also by applying a cumulative distribution function on this, okay, and the same variable W would have resulted Pv y dy, okay, and this we would have written as f of v with respect to the variable v. Now if from these two equations, okay, I eliminate W, okay, can you tell me what results? I get V as Fv inverse of Fu u, because, okay, V is nothing but what? V is nothing but the V is the output function, okay. So what we will do, what is the physical interpretation of this one? Convert, the physical interpretation is convert the original image U into a histogram equalized image. Fu of U is the histogram equalized image by applying the cumulative distribution function of U, okay. Now for the case of V, okay, the probability density function is known to you. I have given you the PDF of V. From the PDF of V, it is possible for you to calculate the cumulative distribution function of the variable V. So if the probability density function is of this nature, the cumulative distribution function can be obtained, supposing this is the cumulative distribution function, so that if this is the if this is V, then this would have been W. Now already what I have done is, okay, from the U image, originally I was having U image and I have transformed it to an image W, okay, by applying a transformation of this nature. So from U I have mapped to the W space, and now if I go over to the W and apply an inverse transformation so that I map it to the V space, okay, then I am designing a transformation from U to V. I am just going through W. I am just going through the equalized image W, and really speaking, if I know the nature of these two curves, if the FUU is known to me, okay, or rather in this case if VV is known to me and if FUU is known to me, if the two cumulative distribution functions are known to me, then I need not even physically obtain the equalized image. Even without physically obtaining the equalized image, okay, I can design this transformation, okay. So this is what results, okay. So W is a variable which I have got by mapping U into this W, and I would have got, if I had got the image V, I would have mapped it into the same variable W. So what I am simply doing, from U I come to W, and from W I apply an inverse transformation to come over to V, because V I can clearly write as FV inverse of W. And what is W? W is nothing but FUU, okay. So clearly this is what I get, FV inverse FUU. So that all that I need to know is this transformation function FUU and this transformation FV. If FV is known to me, FV inverse is also known to me, okay, and I get the processed image V. Alright. So given any input probability density